An important application of linear algebra is the study of dynamical systems, and we're going to spend a little time talking about that. We're going to start with a couple of sections from Chapter 8, which introduce the concept of a dynamical system, and then the very important notion of eigenvalues and eigenvectors. And then we're going to jump ahead to Chapter 9 and have a little bit more of a discussion of these things. So the basic idea is we're interested in solving differential equations, and a typical differential equation of the form f prime of t is equal to a f of t, where a is an arbitrary, some given constant. And this is a differential equation and it's a differential equation for the function f. And what that means is, well, it involves the differential. This f prime is just another word for df dt. So another way to write it is this. And so I'm saying, I'm describing a function f in the following way. I'm saying, please tell me a function f whose derivative is a constant multiple of itself. And this is a differential equation because it involves a differential. And the solution is the function f. The question is, what f makes this true? And I think you all know this, or maybe you knew it at one time and will soon be reminded that the solution to this is, well, you can take f of t to be e to the at. And not only that, you can let it be this times an arbitrary constant c, where c is any constant. And let's check. Why is that true? Well, let's see. If that's f of t, what is f prime of t? Well, the derivative of this function is c times the derivative of e to the at, which is a e to the at. And you can pull the a out front to make it a c e to the at. All I did was switch the order of the constants. And this right here is f again, c e to the at. C e to the at. So this thing is indeed a times f. Okay, so that's just a quick reminder of a basic problem in Math 140. And there's a little bit of linear algebra in this problem, but not so much. But here we're going to talk about a generalization of this, where we have a system of differential equations. And a typical thing is you give me a 2x2 matrix A, B, C, D, and what we're looking for is a pair of functions, f1 and f2, which are supposed to satisfy. Well, let's see. So it's a pair of differential equations. So I want f1 and f2 prime. I'm going to describe them, and I'm going to ask this. So this would be just like what I had before. f1 prime is a times f1. But I'm going to ask that it also involve f2. And f2 prime is c times f1 plus d times f2. So this is what we're going to be talking about quite a lot. This is a 2x2, particular kind of 2x2 dynamical system. Or, in other words, it's a 2x2 system of differential equations. And f1 and f2 are linked, so this really is a linear algebra problem, and we're going to spend a fair amount of time talking about this kind of equation. So here is the system of two equations that I'm trying to solve. Again, I'm given these four constants a, b, c, d, and I'm trying to find f1 and f2. The first thing I'm going to do is to think of this as a vector equation, which is to say I make a new function. F of t is this pair of functions, f1 of t, f2 of t. So what is this f? This f is a function. The input is a single real number, and the output is a pair of real numbers. So it's a function from R to R2. And you can think of this as being some sort of curve. This is f of t. As you vary t, you move around and following some curve in the plane. Okay, so how are we going to solve this equation? Let's remind ourselves when you just have one equation, if I just had f prime of t is equal to a f of t, I saw that the solution was f of t is equal to c e to the at. Some sort of exponential. So I'm going to now follow the time-honored tradition of guessing a solution to the pair of equations. And the idea is the following. I'm going to guess that f of t is equal to some exponential e to the lambda t times some fixed vector x naught y naught. Okay, so I'm guessing that the solution is of this form. And what does this say? Well, the analogy is that this x naught y naught here is analogous to this constant, and this exponential here is analogous to this exponential up here. So instead of an exponential times a constant, I'm talking about an exponential times a vector. And the picture is the following, that you have some vector. This is the vector x naught y naught. And then f of t is what? Well, you're multiplying this vector by some scalar. And, for example, if lambda is positive, as t goes to infinity, this scalar is getting bigger and bigger and bigger. So you should think as you're moving exponentially along this line. This is f of t. Okay, so, well, it's just a guess. I have no solution. I have no idea whether such a thing will work. Well, actually, I do know, but what do you have to do? You have to guess that this is a solution and try to find x naught, y naught, and lambda, which make the original pair of equations true. So let's see. I'm guessing that f is of this form, and I can pick x naught, y naught, and lambda, which make this true. Well, this is this pair of functions. So what are f1 and f2? F1 is the first coordinate, which is to say x naught e to the lambda t, and f2 is y naught e to the lambda t. So let's just plug these in up here and see what we get. So f1 prime is x naught lambda e to the lambda t. That's what happens when you take the derivative of this. And I'm hoping that that's going to be equal to a times f1 plus b times f2. And similarly, the second equation, f2 prime, is y naught lambda e to the lambda t. And I'm hoping that's going to be c times this thing plus d times this thing. Okay? So that's what I'm trying to solve. I'm trying to find lambda, x naught, and y naught, which make this true, both of these equations. Well, here's the beautiful thing. E to the lambda t occurs in every term. And it's never zero. An exponential is never zero. So you can simply cancel all of the e to the lambda t's. Ha! What do you get? You get the equation x naught lambda, y naught lambda is equal to a x naught plus b y naught, c x naught plus d y naught. And now that is a purely linear algebra statement. There's no functions. There's no t. There's no e to the lambda t. X naught, y naught, lambda, a, b, c, and d are all constants. So this is a pure 2 by 2 linear algebra problem. And exactly what problem is it? Let's write it as a matrix equation. I'm going to switch the two sides, and I'm going to say that a, b, c, d applied to the vector x naught, y naught, that's this thing, a, b, c, d, x naught, y naught, is supposed to equal the vector x naught, y naught times the constant lambda, which is to say x naught, y naught. Okay, so that's what I'm trying to solve. And again, I'm trying to solve this for lambda, x naught, and y naught. Now let's stare at this for a second. X naught and y naught appear on both sides of this equation. If they didn't, this would just be a standard thing. You'd have a matrix times a vector is equal to some other vector, and you'd solve it. Try and take the inverse or whatever. But this is a little different. The key point here is that this vector, which I don't need a name for it. This vector here occurs on both sides. So it's a little bit different from what we saw earlier in the semester. If I write this out as I can, in shorthand, if I call this vector V and I call this matrix A, I've got the equation A times V is equal to lambda times V. And this is a very important kind of equation. This is an eigenvector and eigenvalue equation. I'm given the matrix A, I'm looking for a vector such that when you hit it with A, you get a multiple of that vector. And notice that I have to find both the vector and the multiple. So there are really three unknowns here, as I said right here. Anyway, that is exactly the type of equation we're led to, and that leads us directly into eigenvalues and eigenvectors. So one way to think of these eigenvalues and eigenvectors is that this matrix, when it acts on R2, it stretches by a factor of 2 in this direction, and it just stretches by a factor of 1 in this direction. It doubles the length of this vector, and it keeps that vector the same. Now here's another closely related example, which is the matrix -1, 2, -3, 4. Suppose I asked you to find eigenvectors and eigenvalues for this matrix. Well, we don't know how to do that yet, so let me just tell you the answer. If you plug in 1, 1 here, you get -1 plus 2 is 1, and -3 plus 4 is 1. So that says that 1, 1 is an eigenvector with eigenvalue 1. And if you plug in 2, 3, you get -2 plus 6 is 4, and -6 plus 12 is 6, which is 2 times itself. So 2, 3 is an eigenvector with eigenvalue 2. Now, I think you can see by this example, it's not so obvious how to find these things. We'll talk about that. But in any event, I want to draw a picture. And the picture is you take the vector 1, 1, and let me draw it a little smaller so I have room. Take the vector 1, 1, and take the vector 2, 3, and we're multiplying by a factor of 2. This vector is being doubled, and we're just multiplying by 1 on this vector. So this matrix is acting by stretching by a factor of 2 in this direction, in this basis, just like this one is stretching by a factor of 2 in this basis. And So in a sense, these two matrices are extremely closely related. This matrix and this matrix are really doing the same thing, just in a different basis. And the eigenvalues and eigenvectors are telling you that, and they're telling you that these once you found the eigenvectors, it's sort of easy to visualize how this matrix is acting. Okay, so that's a couple of examples. So one way to think of these eigenvalues and eigenvectors is that this matrix, when it acts on R2, it stretches by a factor of 2 in this direction, and it just stretches by a factor of 1 in this direction. It doubles the length of this vector, and it keeps that vector the same. Now here's another closely related example, which is the matrix -1, 2, -3, 4. Suppose I asked you to find eigenvectors and eigenvalues for this matrix. Well, we don't know how to do that yet, so let me just tell you the answer. If you plug in 1, 1 here, you get -1 plus 2 is 1, and -3 plus 4 is 1. So that says that 1, 1 is an eigenvector with eigenvalue 1. And if you plug in 2, 3, you get -2 plus 6 is 4, and -6 plus 12 is 6, which is 2 times itself. So 2, 3 is an eigenvector with eigenvalue 2. Now, I think you can see by this example, it's not so obvious how to find these things. We'll talk about that, but in any event, I want to draw a picture. And the picture is you take the vector 1, 1, and let me draw it a little smaller so I have room. Take the vector 1, 1, and take the vector 2, 3, and we're multiplying by a factor of 2. This vector is being doubled, and we're just multiplying by 1 on this vector. So this matrix is acting by stretching by a factor of 2 in this direction, in this basis, just like this one is stretching by a factor of 2 in this basis. And so in a sense, these two matrices are extremely closely related. This matrix and this matrix are really doing the same thing, just in a different basis. And the eigenvalues and eigenvectors are telling you that, and they're telling you that these once you found the eigenvectors, it's sort of easy to visualize how this matrix is acting. Okay, so that's a couple of examples. Okay, so suppose I give you a matrix A, n by n, and I ask you to find an eigenvector for it and its corresponding eigenvalue. How do you do that? Well, let's write down what you're trying to do. You're trying to find a vector such that AV is equal to lambda V. Now, remember that V, which I'll write as A1 through AN, and lambda is what we're trying to find. So they're really n plus 1 indeterminates. And I mentioned before, it's crucial that V appears on both sides of this equation. So if I had an equation AV is equal to a fixed vector, I could solve that. So, well, that sort of tells me what to do. Move this to the other side. This is the same thing as saying AV minus lambda V is equal to the 0 vector. Okay, now I have a matrix equation that's kind of more familiar to me. I'm trying to find the kernel of something. And this AV minus lambda V, well, notice that lambda, the scalar lambda times V, is just the same thing as this times V, which is to say lambda times the identity matrix times V. So I can rewrite this equation as A minus lambda times the identity is supposed to take this vector to 0. So this is a crucial equation. Well, remember, I'm supposed to be finding both lambda and V. Well, when does this have a solution? Of course, I can always take V to be 0. Taking V to be 0 on both sides of this is always a solution. And I should have said we're only interested in non-zero solutions. So when does this equation have a solution? Well, this matrix, A minus lambda times the identity, better be singular. This has a solution, V not equal to the 0 vector, if and only if the determinant of A minus lambda is 0. Right? That's what it means to be, that's our condition for it to be singular. And so this tells me how to find lambda. Solve this equation for lambda. V has nothing to do with it. This is just an equation for lambda. Then once you find lambda, plug that back in here, and then find V. So that's basically the big theorem from this section. And this is really an extremely important theorem in linear algebra. If you have a matrix A, then the first statement is that lambda is an eigenvalue of A if and only if the determinant of this matrix is 0. And secondly, given such a lambda, the corresponding eigenvectors with eigenvalue lambda are exactly the kernel of the matrix A minus lambda times the identity, which is to say, i.e., the vectors which satisfy A minus lambda times the identity applied to that vector is 0. Okay, so I suggest that you think about this. Well, we'll do some examples, of course, and but this is an extremely one of the most important results in the whole course. So let me conclude with this example from before. I did this one before, and I'll show you how I got it. So take A to be the 2x2 matrix, and I'd like you to find every eigenvalue, and for every eigenvalue, the corresponding eigenvectors. So, well, you take this A minus lambda I, which is to say minus 1, this matrix. Lambda times the identity is this. And so you just take the matrix that you started with and you subtract lambda from the diagonal entries. And you take its determinant, 2 minus 3, 4 minus lambda, and you ask whether that's 0. Well, what is the determinant of this matrix? It's minus 1 minus lambda times 4 minus lambda. Minus some minus 6 is plus 6. When is that equal to 0? Let's see, you get lambda squared minus 4 lambda plus lambda is minus 3 lambda. Minus 4 plus 6 plus 2 is equal to 0. And lo and behold, that's lambda minus 1 times lambda minus 2 is equal to 0. So you found this lambda is being 1 or 2, as I told you earlier. And you go over here now, and let's say take lambda is equal to 1. Well, you take this matrix right here, and you plug in lambda is equal to 1, and you get minus 1 is minus 2, and 4 minus 1 is 3. And to find the corresponding eigenvectors, I'm trying to solve this is equal to 0. I want to solve this for x and y. And, well, it's you can just stare at it and you can see that the answer is x is equal to y. In other words, the vector is xx. And, well, of course, this is all this is multiples of the vector 1, 1. And so you can take for your first vector the vector 1, 1, but you can take any multiple of that too. You can take any xx. And for the second eigenvalue, this corresponds to lambda is equal to 1. And when lambda is equal to 2, when you plug in lambda is equal to 2 here, lambda is equal to 2, you get minus 1 minus 2 is minus 3. 4 minus 2 is 2. And we're trying to solve this is equal to 0. And you just stare at that for 2 seconds, and you see one possible solution is xy is equal to 2, 3. So that's the eigenvector. That's an eigenvector with eigenvalue 2. And just like before, xy I could have taken to be any multiple of this. I could have taken 2c, 3c for any c. But anyway, there's an eigenvector with eigenvalue 2, and there's an eigenvector with eigenvalue 1. All right, I think that's a good place to stop.